Okay, why don't we go ahead and get started to leave enough time for both of our speakers today. Kevin Chen from TAC is going to be giving our first talk on integrating scientific tools and web portals using Diagrid. So Diagrid's been used in several ECSS projects very successfully. It's very adaptable to use by many different applications. And I look forward to Kevin's talk today. So with that, why don't you take it away, Kevin?
All right, thanks. Thanks, Nancy. And good morning, everyone. My name is Kevin Chen. I'm a staff member here at TAG. So in the next 20 minutes also of today's talk, we'll be talking about the progress we made on developing scientific tools on Diagrid web portal. Okay, here's a simple outline for today's talk. We'll start out with a brief introduction on Diagrid, and basically we'll be covering the stuff on why we're using Diagrid as a platform, and that's followed by the service provided by Diagrid, what kind of service Diagrid can provide as a scientific portal and as a user, or for both users and developers, how do we take advantage of that kind of service? Towards the end of this talk, if we have enough time, I'm going to cover we're going to showcase two examples in terms of tool development. The first tool is the molecular dynamics simulation tool called GROMACSIMUM, and the second tool the second tool is the interactive parallelization tool called IPT. Okay, what is Diagrid? And Diagrid is a instance of HubZero platform, which is currently developed and maintained by Purdue Research Computing. The reason why we pick Diagrid as the platform at the web portal for our tools is that, first of all, back to years because I was there as part of a core development team of Diagrid. That's basically where the story come from. And speaking of the advantage of using Diagrid as a scientific portal, as a user, you can and Diagrid provide a great platform for collaboration and community building features, such as a user you can do the collaboration and show your data and do the visualization with your collaborator and the colleagues. And Diagrid provides service, software as service features to all users, which means as a user you get access to a large amount of computational resource, including the HD control pool, exceed computational resources, and Purdue local HPC cluster computational powers. And also, as a user, you don't have to do any local installations. Everything is done through the web portal. As a developer, of course, you can develop. You can take advantage of the large amount of HPC or HD control computational resources tied behind the portal, and also you can take advantage of a predefined pipeline to speed up the whole development process. Based on my experience, to develop tools on Diagrid is much easier comparing with all other portals currently available on the market. And also Diagrid make the tool development process a lot easier. For us as a developer, this is pretty important because that will save time and energy in terms of publishing our tools on Diagrid interface. And also, Diagrid provide a whole set of features in terms of communicating with end users. They're supporting a ticket system, they're supporting social media and blog kind of features, and also they allow user to post questions and wish lists on the tools, on existing tools, and in that way, as a developer, we can get back to a user in many different useful channels. And as you can see here, the diagram at the bottom of this page, and as a developer, we can do the development using multiple all kinds of programming languages such as Java, Python, R, C++, and once your tools get developed, you can push it out through the portal interface. And as a user, you can basically share your data, uploading your data, and do the science, do the calculations, and at the end, you can see your result through a simple web interface. Now, speaking of the hardware behind the diagram, as mentioned briefly in previous slides, all the diagram tools can be supported to all diagram jobs can be sent to either HD counter pool. The HD counter pool tied with the diagram portal is combine the free cycles all across 10 research-based university and institutions, and we have up to which can provide up to like thousands for computational hours at peak performance. And also diagram jobs can be run on C resources such as Stampy and Comet. And most importantly, as reliable HPC resource, all jobs can be run on Purdue local clusters such as Coase, Roseman, Hansman, and Carter. And numbers speaks for themselves. Today, we have over 100 million jobs run on diagram through variety kinds of tools. And here's just a quick peek about the interface once your diagram account get established. And as you can see on the left-hand side of the screenshot, we have this like a user dashboard type of setups. You can do, you can configure your profiles, set up your account, and you can create groups and set up permissions for certain users. To control the accessibility of certain tools, you can allow or disallow the user to use your tools, and those can all be done through there. And through the contributions, you can earn points and run more jobs. Of course, there's a way you can show, you can present the usage metrics about the tools you're interested in or you're developing. And of course, you can through the message board, you can communicate with both user and diagram supporting teams. On the right-hand side, you can see here's the message I got from the system in from diagram, showing my tool is ready to get improved. The similar way, you can contact with the user, answer user questions, concerns, or provide suggestions or tricks in terms of how to use your tools. Last but not least, diagram supports all those social media features such as blogging. You can show other people how the progress, what kind of progress been made through the development phase, and share the ideas and the tricks with your fellow colleagues and coworkers. And basically, the way how diagram using is coming into play as the portal is showing this diagrams, as shown on these diagrams. As user and developers, you can do the visualization, you can upload your tools, you can run the tools, you can do the analyze, and you can earn points, and then you can do training and teaching sessions, and most importantly, you can do research on diagram using those existing and scientific tools. The way how it get done is like you can provide a user input and through the web interface, and all those jobs, once those input get collected, it can be sent to remote HPC or HT counter computational resources. And once those jobs get getting done, and it can be transferred back to the hub And in that case, user should be able to visualize the result and go from there. Here's just a quick peek on what the diagram looks like once you log in. And currently, diagram supporting different kinds of web applications. And diagram support, we support the traditional web applications written in PHP, JavaScript. Those what we call as components. Those for however, that's not the interest for current today's this topic. So on today's topic, today's talk, we mainly focus on those standalone applications which can be developed by Java, Python, or C++. Basically, you create a simple GUI user interface, and you tie your standard applications in there. You run everything through the web browser through a remote desktop kind of environment. That's what we call is like a diagram VM. And speaking of web browser support, we support Java application through Java applet. And if your browser doesn't support Java, such as Google Chrome and stuff like that, we do support HTML5 to provide a seamless visual experience. And that all being said, there's no local installation is required because everything is done through the web interface. Now here's the simple workflow in terms like a deployment, deployment. At the beginning, as you can see here on the right-hand side, this chart, as a developer, we can develop our applications. For this case, we can use Java, Python, all those kind of languages. Once you think your tool is ready to be published, and then you can upload your tools through the web interface again. And this can be tested once your code be successfully uploaded, and you can do some testing, and you can ask your colleagues to do testing as well. And once you're happy about what you've seen and so far that stage, you can approve it. And this once you send a message by clicking a magic button, once the button gets clicked, and the message is going to send to the diagram system admin, and they're going to come in to publish your tools. This is just so simply put, to publish your tools, just as simple as that. So let's say for the next time you want to add new features or new release with bug fix, you can go through this. We have, I'm sure we have the diagram staff standing by to go through, help you go through this process as easy, as smoothly as possible. So this is just a typical workflow you have experience in terms of publishing tools on diagram. And here's just a quick example about the job submit and meeting value. How does that work? As mentioned earlier, all diagram tools can submit job to either HD counter or HPC resources such as Stampy and Purdue local clusters. And let's take a HD counter job as an example. And here in this diagram, we showed you guys how to use the unified submit mechanism built in from diagram portal to submit HD counter jobs. As a tool developer, you within your tool, you're going to collect user input. Once all those user input get collected, you can do some pre and post processing. Once the tools think the job is ready to get submitted, now we're going to go through this unified submit mechanism. The reason why I call it unified is because it doesn't matter where the job is submitted to. Either your job is submitted to local diagram server or remote host like HD counter pool or Stampy attack. They all through the same submit command and channel. As a developer, all you need to specify is the destination where you want to submit your job to. And once that process gets started, and there's a built-in and back-end work Pax's workflow mechanism, workflow management system to manage all those job submission and to make sure that our jobs get submitted to the right host and they're running okay. And then they're gonna, once the jobs are running, they're gonna monitor all those jobs. Once the jobs are done, once their calculations are done, they're responsible. The system is responsible to copy all your results back over to Integrate web portal for a user to do further analyze or visualizations. And in the next couple slides, we're going to show you guys one example of the scientific tools we developed called GROMACSIMUM. From the name, probably you can tell this is got to be something related to the one of the most famous MD simulation tool called GROMACS. So basically, this tool is all about creating a GUI interface on the existing famous GROMACS MD simulation tool called GROMACS. So based on our experience in the past, given the complexity of MD simulation system, the way how they get set up, the way how they get submitted to the HPC resource to run is extremely complicated, and that will prohibit, especially for those people who don't have a whole lot of experience in the past, for both HPC or computational chemistry. For those people, it's really hard to pick up to get going. So we come back together and say, why don't we do something to help those people to go over those barriers, and in terms of developing a tool to help them go through this whole process. So the way how this tool is going to work is that we have built-in workflow to get you through every single step of MD simulation setups. For this case, it's going to be the GROMACS simulation setup process, and every single step was covered by using GUI interface. And the goal for this tool is that eventually we could help those users who don't have a lot of experience in MD simulations can work along with all those pre-prepared workflows. While for those experts who had a lot of experience using MD packages in the past, can enjoy a significant relief from the tedious of typing and scripting. And the main frame of the tool is going to be look like something like this. As you can see here on the left-hand side, we have a project management panel, which you're going to have all your source code and source file and input file and output file showing here. Obviously, you can create different project based on the system you're working on. And on the top, we have a few menu selections in terms of file transfer and project management and command management and simulation setups and help. On the right-hand side, we have this thing so-called a multiple function panel. And here we show the 3D structure of a given protein structure. You can do the selections. You can change the way how this thing got displayed. This is done through a JMO object. Obviously, the reason why we call it a multiple function panel is that you can do, instead of doing visualization on 3D structure of protein, and you can also do the file editing. You can use that as the file browser. You can edit all those input files. You can change the parameter settings for simulations, and also you can view the plots or figures showing up at the end of simulation, which we'll get into in just a second. And due to the time limit, I'm not going to have enough time to do the live demo today. Herein, we're just going to highlight a few of the key features come with the tool. The first thing I want to highlight is the way how you import your structure. You import your protein structure. There are 4 ways provided through this GROMACSIMUM tool. First of all, if you have your structure ready, you can upload them through the web browser. Just if you have your protein structure ready on your local computer, this can be done by just one click away by uploading your structures through the web browser. That's this from computer means. And if you have your protein structure saved on the diagram hub, that being said, once your diagram and getting created, you get a 10 gig byte space by default, so you can save lots of stuff in your home directory. If you have a file over there, you can navigate through the diagram hub through the school interface. And if you want to get your PDB structure or a mode structure from the PDB bank, you can do that without going to the going to the website, PDB bank website. All you need to do is just provide the 4-character of identifier of a given structure. And once the identifier get supplied and you click the import button, the structure can be imported. And the successfully import structure can be showing on that project pane on the left side of your multiple function panel. Also, if you have, let's say you have your structure, you have an input structure, protein structure on a remote host on Stampy, all you need to do is just click that from SSH button and input the host name as Stampy and your username, port number, the location on Stampy, and you can import your structure over there. One of the most important, the most challenging part is like to support every single built-in GROMACS built-in module within the tool. And at the beginning, we just wanted to support a few of them, but we feel like it'd be nice if we can do all of them. But the challenge here is that every single built-in module or battery files come with a different number of options and different options at all. So we spend a lot of time to be able to support all of them. And as you can see here, is this is kind of beefy top menu tab on the top of this page, because we have to support almost 60 plus modules within our GUI interface. And luckily we're able to get done for all of them. And we understand that even for a long-term, like a empty GROMACS user, probably you don't necessarily remember every single option of that, what that means. And the nice thing about our tool is, like, if you hover over your mouse over one of the given options, we're gonna have a nice tooltip showing what does this option means and what kind of input parameters you're expecting as a user to supply. And speaking of job submissions, as a user, you no longer need to deal with all kinds of HPC or HD counter job schedulers. It doesn't matter if your destination host is using QSub or Slurm or HD counter. All you need to do, just as a user, you just need to pick the destination where you want your job to be run. And for this case, you can select the diagram. You want to run the job locally, or you can pick Purdue clusters. We're going to send the jobs. If that's been selected, we're going to send the job to one of the Purdue HPC resources. Of course, we get an option to support for running jobs on XC resources, such as Stampy. On the top of this window is showing the automatically generated job submit script for you to double check to make sure our tools pick up all the necessary input parameters for MD runs are correctly set it up. And the next thing you need to do is just a number of processors you want to run your jobs on and how long you want to run those jobs. And also you get the next little options to send an email once all those jobs are done, to let you know, oh, your job's done. And once the job is submitted to the remote host, you get a chance, you get the ability to monitor your jobs, and you can cancel them, you can put them on hold, and you can do all kinds of stuff from there. And what's probably the most important thing about doing MD simulation is to be able to carry out the post-analyze, to show the figures to your colleagues and to represent them in the scientific publications or research conference. And from that perspective, we have built-in J-free chart of windows within our tool, can do basically all the kind of analyze and plotting, and can do them on the fly. Whenever you have the results and come back from the remote host, we should be able to present that within our tool. And we do understand that some researchers do have their personal preferences in terms of using the third-party software such as XML Grace, VMD, and PALM, and a whole bunch of other stuff. If you prefer to use that, you don't have to exit from our tools. We do have a seamless connections for allowing users to do all those to launch VMD, GROMACS, XML Grace, and PALM within our GROMACSIMUM tools. And here's just some usage metrics since the tool got released about 3 years ago. Today we have almost 100 users come from all parts of the world, including Asia, Africa, Europe, and North America. As you can see, we have like 10%, 20%. We have equally distributed usage group from all over the world. And if you look at those numbers too small, we see we have users we have K-12 users, we have college students, we have researchers, we have teachers and students, all kinds of users through the course of these tools. And in terms of number of jobs being running today, we have over 13,000 MD simulation jobs running today, and that number is still counting. Okay, let's talk about the other tool really quick. This tool is called Interactive Parallelization tool. This is collaboration between us with PI Ritu Araya, who's also a colleague here working in UT Austin. What this tool is about is to allowing user to convert your serial code into a parallel format. The way how this works is like from the diagram interface, you're gonna, as a user, you can provide a working version of serial code, either in C or C++. That's what we support as we're speaking. And we do have a plan to support Fortran in later times. And once those codes get uploaded, and we can do the magic thing to convert it into either MPI or OpenMP or CUDA writing code for you guys to test. And the reason why this is basically the tool is called, we call it IPT. This IPT tool is we call it as a semi-auto tool that can be used by domain experts and students to use to convert your serial code into a parallel format. The reason why we call it semi-auto because given the complexity of parallelizing programming, we have to get the user to involved to do selections in terms of which for loop you do want to parallelizing, and which one you want to do it, which variable you want us to do parallelizing for, and lots of questions need to be answered on the fly once the job gets launched. Here's a quick pick about what this tool looks like. So comparing with the GROMACSIMUM tool, the interface for this tool is a lot simplified, because basically we only need 2 steps. The first step is like involving the tool uploading and the questions that users need to be answered. And the second step involving once the tool is getting converted, and if you want to test your tool newly generated parallel code on one of the remote hosts, you can submit those MPI or OpenMP ready codes to the remote host for testing purpose. And here's just some quick questions, some like snapshots in terms of how this like question involved, user involved steps looks like. And on the left hand side, we have MPI type of conversion, the type of questions you're expecting if you want to convert your code into MPI format. And on the right hand side, we have OpenMP examples in terms of like how do you want to convert your code into OpenMP ready format. And this is a nice little tool, works for all the basic situations. If your tools like if your code is like too complicated, probably you're gonna sit in there like half day to answer the questions. But for the simple test case or teaching user or students how does like the parallelization work in your code, that's a good start point. And looking at that's all I have for those two tools. Looking for the futures, as I'm sure Diagrade development teams are always looking for a partnership. If you or anybody who around you looking for a platform to start collaboration, or you want to like you're looking for a platform to be the hub of your future scientific developing works, Diagrade definitely is the is one of the best places out there for you guys, available for you. My roles obviously have changed because I'm no longer a team of no longer a member of the Diagrade development teams. So my roles gradually shifted from the developer to the contributors. I'm still come back to the Diagrade and do all this nice works, and hopefully we get stuff, good stuff done in the near future. And if you have any questions, the PI for Diagrade project is Kara Song at Purdue. You can contact with her directly. If for some reason she is not reachable, I'll be happy to forward any questions if you have in terms like publishing your tools on Diagrade. With that, I'm ready for questions and comments. I think that's all I have.
Kevin, thank you very much for a very good talk. Why don't you stop your screen sharing and we'll have Jerome get his going while we're taking any questions from the audience. Does anybody have any questions for Kevin? I thought that was a very interesting talk.
Yeah, hi Kevin, this is Mona. Can you hear me?
Yes, sure. Go ahead.
Thank you for that talk. And I was actually thinking, so Diagrade seems general enough to accept any type of applications, or is it mostly for molecular dynamic type of applications?
It doesn't matter what kind of applications, they can do it all. But those just like those examples I show here today are like MD simulation related tools, but they're not restricted to any science domains or any kind of tools. What I like most about the Diagrade as a scientific portal is that the huge HPC resource tied around behind. Unlike other tools, you have to bring your own like allocations and all those stuff, but the Diagrade makes it like very straightforward and easy for developers, for both developers and users. Does that answer your question?
Yeah, it does. So then my next question is, how does it handle large amount of data, like hundreds of gigabytes or even terabytes? Is there support for that level of data?
That I think is a work in progress. And right now we're dealing with like several gigabyte and tens gigabyte data without any problem, either through the web portal or we have this built into, we actually developed a couple tools allowing users to transfer data. And in the long run, I think we had this conversation many times when I was still at Purdue, is to support global stuff for data sharing and large data transfers. And I think that's where we want to go. If you want to pursue this with Diagrade, you're more than welcome to contact with the Diagrade people, such as Kara Song, who's the PI for this project. I'm sure they have a detailed information you're looking for in that domain.
Okay, thank you very much.
Sure, you're welcome.
Great, thank you very much, Kevin. I think we'll have to move on to our next speaker, but Kevin's contact information is on the symposium website if folks have additional questions for Kevin afterward. Thanks for a very nice talk, very much appreciated. So Jerome Bien, also from TAC, is our next speaker, and Jerome's going to talk about work he's doing with the distributed multi-threaded checkpointing software package. This is really a nice example in ECSS where we work with the actual code developers so that the improvements that we can make go into the code that's then used by many, many more groups. Jerome, I think, is going to talk about his OpenSHMEM implementations, and this work has also been featured in 3 different papers, and very much looking forward to hearing about this today. Why don't you take it away, Jerome?
Okay, thank you. So yes, so my name is Jerome Bien. As one introduced, I am a research associate at TAC, and I will present the ECSS project that I currently have with Professor Jean Cooperman from Northeastern University. But the funny thing is how this ECSS project started. So every year there is a meeting called MVA Pitch User Group Meetings. And 2 years ago, I was doing a presentation about scalability and optimization of MVA Pitch 2 as this meeting, and Jean was there. And the year after, he was also presenting he was presenting the MTCP to this meeting, and he came to me because he had some issue with some scalability issue with the MTCP, and he told me, "Oh, we are planning." So he came to me and he told me, "Nice to meet you. My name is Jean, and we are developing the tool, the MTCP. We have some issue, and we are planning to submit ECSS project to have access to Stampede, and I was wondering if you can help us to fix some of the issue." I mean, it was very basic issue at the beginning. I told him, "Yes, it's not a problem. We just send me an email when you have access to ECSS, and we can just exchange some email, and I can give you some magic flags that I know to make the thing scalable." But talking with him over the conference the day after, etc., I discovered that this small issue, behind this small issue, there was a lot of big issue that was requesting much more time. And I told him, "You should start to do a ECSS project," and he didn't know what was the ECSS. So I explained to him, I gave him the link. When he came back to Northeastern University, he explained, he told me that he was very interested to use that to allow me to work with him, to have much more dedicated to work with him. And we worked together on this part inside the ECSS proposal, and he submitted the proposal. The ECSS proposal was accepted with the ECSS support, and since this, we started to work together in January with bi-weekly meetings. So we have a conf call every 2 weeks to talk about progress, issue, etc. And as you will see, this collaboration has been very productive. So, but before to do a very quick overview about what we did, because it's very difficult in 20 minutes to cover 3 papers and all the work that we did together. Initially my presentation has probably 85, 90 slides. So I had to cut to get something that could fit in 30 minutes. So we will see, sometimes if I have too late, I will probably speed up a little. So first of all, what is checkpointing? So checkpoint restart is the ability to save a set of running process to a checkpoint image on the disk and to later restart it from the disk. So checkpoint restart involves saving and restoring all the user space, the memory state of all the state, kernel state, network state. So when you do your checkpoint, you checkpoint also the status of the communication when you are sending a messages, how many package has been sent and how many are still need to be sent, etc. So you have to checkpoint everything. And why do we need to use checkpointing? So the first thing that you can think is a fault tolerance. So what's to avoid hardware failure when you are running a code for a long time. But there is multiple usage that can be done with checkpointing. It can be done for scheduling and process migration. So, for example, before maintenance, if you want to checkpoint, and if you know that your code won't run until will be cut during the maintenance, before the maintenance, you can just stop the code and do a checkpoint and restart after. For a faster startup time, because sometimes you can have a code that have a long initialization process, and whatever is your input is initialization process can be the same. So why not just checkpoint just at the end of this process, and you will save this time for the second time. You can save and restore workspace, so managing tails for multi-thread application, for debugging, as we will see later, for speculative execution. What's happened if I do that, etc. You can vary your input and restart the job, etc. So, DMTCP. What is DMTCP? So, as I introduced, it means distributed multi-threaded checkpointing. So it's an open source system level checkpointing. It's totally transparent to the user. It works without any modification of the source code of the binary. It's user space level, so you don't need to apply a kernel module or something like this. It handles distributed application with a centralized coordinator. So globally, when you want to use DMTCP on 64 nodes, you will have to ask for 65 nodes, one that will run the coordinator, and your 64 other nodes to run your code with DMTCP. And the coordinator will manage all the checkpoint, etc. It supports multiple programming languages, C, C++, Java, as well, Lisp, etc. During this collaboration, we added also the support of OpenSHMEM. It handles multiple kind of MPI libraries, resource manager, process manager. So I was able to use DMTCP with OpenMPI, MPI-2, Intel MPI, etc. So if you're interested to use DMTCP, this is the website, http://dmtcp.net. So let's start to this presentation. So there will be 3 parts. So I will try I will be fast on this part, but I provide you the link of the paper that are related to these parts, and if you're interested and if you want to dig a little more. So the first one is extended bash session and 3-phase debugging. So how we can use DMTCP to extend bash session and how we can use it to do some debugging with a special process that we designed called 3 phases debugging. How to checkpoint restart with OpenSHMEM. I will explain you how we end up to that. And the initial work that I was supposed to do with Jean is system level scalable checkpoint restart. It's for petascale computing, but basically it was how to fix the scalability and how to fix how to support some features of MPI library to run very large-scale experiments. And before to go on the final conclusion and the future work, because this is the work that we did, we still have plenty of work on the to-do list with also a lot of paper that we are planning to do, which is very nice. So first of all, extended bash session and fast debugging. So the first thing is, as I told you earlier, people think mainly about fault tolerance, using checkpoint for fault tolerance. But when you are scheduling your job, sometimes you can do an over-reservation of your resource due to not a very good estimation of your job, and and sometimes your job terminates before it's over because your allocation time is finished. And it could be also cluster maintenance. When you have a maintenance, some scheduler like we have at TAG doesn't allow jobs that are longer than that will start, doesn't allow job that will run during the maintenance based on the schedule submitted by the user to run if the execution time is longer than the beginning of the scheduled maintenance. But sometimes some admin can just cut in case of emergency maintenance or whatever. And we find a way also to use, and also for debugging, how can you debug a code? For example, if you have a code that is running for 6 or 8 or 12 or 3 days, and you have a bug after 8, 1 day or 2 days, how can you debug it? So if you want to do an interactive session with a debugger, it can be very time consuming because it's not very easy. But the solution that we are providing is to use the system level checkpointing using the MTCP. So what to do with job that might continue beyond the maximum limit set in a batch session? So there are multiple ways that we are able to handle with the MTCP. It can be the use of hooks provided by the resource manager. So to allow to do a checkpoint before the shutdown, because it's possible to know with some batch scheduler what kind of, when the maintenance is scheduled, and to provide a hook, or an admin can distribute, can propagate it, something that can allow the checkpoint to happen. And the question is, how efficient is the checkpointing? And the question is, how efficient is the system level versus application level? So application level, it's mainly the application that is requesting the checkpointing. So you have to, it's done inside the code. When the system level is mainly totally independent. And you can also use timers when hooks are not available. Let's say let's do a checkpoint every 3 hours or 4 hours, etc. And the second one is the checkpoint enable debugging. So what to do with long-running batch job that crash and exhibit other problems. So the checkpoint at runtime, the idea is to checkpoint a long-running job prior to the problem. So it can be a crash, a hang, a premature termination, an incorrect terminate state, etc. And you can also migrate, so you can do a checkpoint to migrate to a debug machine cluster, to repeat, restart, to attach a debugger, to do interactive session. So the idea that we have for the debugging, and so there was a need for a better debugging experience. What to do with long-running batch job that crash and exhibit other problems. Checkpoint, the checkpoint, a long-running job prior to a problem, a better reproducibility, reduction of the problem at its attended, etc. So how to do all these kind of things? So the idea that we had was 3 phases debugging. So globally, you are doing checkpoint until the error occurs. So let's say that you can do a checkpoint every 2 hours. So the phase 1 is I checkpoint every 2 hours until my job crash. And after, what's happened is, I believe that you can annotate, yes. What's happened is, draw here, yes. So you restart from the last checkpoint before the error occurs, and you reduce the time. So instead to be 1 hour, it could be 1 minute. So you restart from the last checkpoint that you did before, and here you are doing a checkpoint every 10 minutes until the error occurs. And after you restart again in single or debug node, or you can restart the whole job. And here it's allow you to start the debugger from here, because before you had to run the debugger in this way, and by using checkpointing you can just have to run the debugger. I mean, just have to wait probably a few minutes before the things occur. So there are multiple scenarios that we defined. So how to stop the draw here? Yes. There. I have to remove the draw. I didn't know that. It's my first time. So, so the first scenario is you submit a job, as I'm explaining, with a frequent checkpoint, and you will start from the checkpoint and take final grand checkpoint, etc. And you copy paste. And after you can use your favorite debugger. This is the things that I explained based on the graph. But there is another way to do the version 2 when you have too many processes that restart on a single node or a small debug cluster. So you can suspend all but one process for a while, and it's not necessarily possible. So the solution is to identify a potential faulty process and restart just the buggy process. So with the MTCP, you can, if you have multiple MPI jobs or multiple process, you can just restart. You have the possibility to restart just one process, which is very, very nice. And of course, it's hard to predict the single buggy process out of 1,000, and there is a lack of determinism, but it's a solution that you can do. The third one is for communication intensive application, how to replay communication to a single buggy process on restart. So the idea is you can add an MPI send receive wrapper with counter and restart and checkpoint with some counter, 100 counter for the phase 1 and 10 counts for the phase 2, and you restart after the final MPI send receive before the bug in the phase 3. So this is different way that that you can do. So globally here, so why we did that? Initially is we have some user attack that are requesting, can you extend my my queue time, because my application need to run for 60 hours or for 1 full week. So usually we can provide that. We just have to request one and we can provide these things. But the MTCP is also a solution that you can do by yourself. So you use the checkpoint just before the end of your batch session and you restart. Of course, you will have to submit 3, 4, or 5 jobs instead of 1. But the advantage is you won't have to wait to get the authorization of the admin, etc. Get the authorization. It can take some time, so it's very good. And the second thing is for debugging application, because there is a lot of debuggers that are available, but when you have a very long time execution job that have a long execution time, it can be very complicated to debug. And what you can do is just do a checkpoint before the before the issue occurs, and like this, your debugging session will only last 10 minutes instead of 10 hours. Because usually when you debug, you are also slowing down the code. So as a conclusion, I will say that the system level transparent checkpointing is useful and practical. As I was said, it can be used to extend the batch session, and it can be used also to debug. So let me clean that here. Errors. So here. Okay. It's done. So the second thing is that, so if you want to know more details, because I didn't provide any numbers, but the checkpoint is very fast, and the checkpoint is very fast, and we explain all this technique in the paper called Extended Batch Session and 3-phase Debugging using the MTCP to run the batch session. It's an ECSS paper that was presented in July this year. So if you're interested to know how to use the MTCP and how to use this feature, just take a look at this paper that is available. So the second thing was a checkpoint to start with OpenSHMEM. So I had to work on the OpenSHMEM project. And I tried the MTCP with the OpenSHMEM code. And we realized that there was some issues. And Rohan, also one of the other students from Gene, was able also to run the MTCP with, I helped him to how to use I explained him how to use OpenSHMEM, and he was able to get the same thing. So checkpointing with OpenSHMEM, so I don't know if you know OpenSHMEM, but compared to MPI, OpenSHMEM is globally global shared memory space when you have process element that we call PE that are communicating. Usually you don't have a lot of PE between have 1 or 2 PE per nodes. So checkpoint restart is not something is not something totally new for OpenSHMEM. There are some work that was done already. But most of this work was mainly at the user level, okay? So with DMTCP, when you have to checkpoint everything when you are running your OpenSHMEM code, you have some, we discovered some issue. So we had to extend the design of DMTCP in few areas in order to support both checkpoint of modern MPI implementation and checkpointing of OpenSHMEM. So the first thing it was support of Unix domain sockets. So because earlier MPI implementation didn't use this Unix domain socket. And the second thing was support for CSV shared memory object. Because inside the MTCP originally only BSD style shared memory region were initially supported. There was a third thing was the support of InfiniBand, but this issue was for UD on InfiniBand, but these things was I will present it later. It's part of the third part of the presentation. So the main issue with OpenSHMEM is as you have so with MPI, usually you imagine that you have a node with 16 cores. Usually you have 16 MPI tasks, and you have 16 separate memory space with MPI. But when you use OpenSHMEM, you have a large shared memory space region. Instead of to have multiple, you have a big one. So we have to support this large memory space. And the other issue that we had also is that HPC cluster like Stampede doesn't support virtual memory. So we have to work on alternative strategy to work on it. And so we run the experiment on Stampede using MBA pitch 2. Yes, it's after. So on Stampede, you probably know Stampede, so I will skip this slide. But so we use the Intel compiler, we use MBA pitch 2X that support OpenSHMEM, and we checkpoint the NAS benchmark, BT and SP with OpenSHMEM support. So there is some benchmark available, there is some NAS benchmark available on the OpenSHMEM website that tell you to do that. So with different kind of configurations, so the process element on different nodes, so globally there was 2 or 3 process elements per node, you can do the math, so it's here, the third column, the number of process per node and the different class, we were able to checkpoint, and when you compare the version without checkpoint and with checkpointing, you can see that there is no difference. The time of the checkpoint is very fast. With the 256 processing element, it was taking less than 2 minutes, knowing that the amount of data was pretty big, as you can see here. So you have the checkpoint time for the NAS BT OpenSHMEM. So it's 2 minutes, knowing that the amount of data per process was around 8.5 gigabit. And restart time is also pretty fast, so it's taking less than 5 minutes to restart on the larger scale. This is the same thing for the NAS SP, so the checkpoint time, the restart time, etc. So, as a general comment, at large scale with 256 process, the total data written to the disk was 2.2 terabytes, with an effective bandwidth of 20 gigabytes per second. In all cases, the checkpoint times are dominant by the time to write checkpoint data to the storage. And the cost for the checkpointing in the state of the application is negligible. So, and we observe that most of the checkpoint image was mainly this OpenSHMEM shared memory region. So as a conclusion, we with DMTCP, so by working on OpenSHMEM, we were able to support, and by working with DMTCP and OpenSHMEM, we were able to improve DMTCP to support to checkpoint OpenSHMEM, and with the capability of setting the state of a non-tier computation for restart. We are currently working on some improvements on a leader election strategy where only one single copy of each region will be saved on a single dot, because currently we are saving, we have multiple copies, so we have a lot of duplication, and which will allow you to reduce the time to write in a backend storage. And if you're interested by OpenSHMEM, and if you want to get more details, I invite you to take a look at this paper, Scalable System Level Transparent Checkpointing for OpenSHMEM, that was presented at the third workshop of OpenSHMEM. So I will try to be very fast. Yes, too much slides. So this is the system level scalable checkpointing restart for petascale computing. This was the initial ECSS project. So what's happening is, by default, MPI libraries are using reliable connections, that's what we call RC. But RC is not scalable, because you need to establish a connection with each MPI task, need to establish a connection with all the other MPI tasks that are outside the node. So when you have a 26 on Stampede, if you want to run 24,000 MPI process, you can have up to 516 millions of connections that can be required. And all these connections are requiring a small amount of memory, like 32 kilobytes, but 32 times 576 million, it's a huge amount of memory that is just used for the MPI memory, so the MPI library. So you don't have enough space for the application itself. So the solution, one of the solutions, because there is a new one now called DC, provided by InfiniBand. But one of the solutions was to use unreliable data ramps. So globally here, you don't need to establish this connection. Everything is done on demand. And it's what is used at large scale by MPI library. But the issue that they had was how to save and reply in-flight data that is present in the IB network at the time of the checkpointing. So how to enable transparent checkpointing to support the InfiniBand UD, sorry. So we work closely with, Jean, I work closely with Jean and people from MVAPitch2 to learn more about how to efficiently checkpoint UD, and we end up to the capability, we added this capability to DMTCP. So the paper is not talking only about that. There is other thing that has been done, but I was not really involved. I was mainly involved with this communication issue at large scale. So at the end, this is some number with some applications. So with HPCG, this is a benchmark used to classify cluster like LINPACK. It's a new benchmark used to classify cluster. We can see that the checkpoint time is very quick, and the restart time also is very fast. You can point to me, yes, but the checkpoint with 24K is very slow and the restart is very slow. Be aware that this number, we got this number where Stampede was in production. So this number, we did this experiment where not during the maintenance, but live. I mean, with other users doing a lot of I/O, etc., and Luster was able to handle it. So we did some experiment with HPCG, with NAMD, so with a checkpoint image here at 266 megabyte and 615 megabyte respectively, with one checkpoint image per process, so 256 megabyte for 8K and for 60K, 650 megabyte. So with NAMD, we run also with the NAS LU. So this is a runtime with and without the checkpoint. So you can see that the overhead of doing checkpointing at large scale is very low. The checkpoint restart trend. So here again, it's number that we got when Stampede was in production up to 16K. And of course, the work that we did work also with other MPI library. We didn't do something specific to MVAPitch2. We did some experiments with 500 process using UD with Intel MPI and OpenMPI, and it was working without any issue. So it was a very quick presentation because I don't have a lot of time to present all these results. But if this paper will be presented at IEEE ICPADS in China in December 2016. And if you're interested by this paper, just let me know and I can send you a copy. So to finish, a final conclusion. So DMTCP is a very interesting project. So, the team, so there is a Jean that is a PI that is working with 2 PhD students and one research associate with Kapil that was a PhD student, initial PhD student that developed the MTCP that has his PhD now. And it's a very productive ECSS project. We have biweekly conf call. Currently we are working on kernel, etc. We will, if we have time today during the Stampede maintenance, we will try to run tonight some large-scale experiment on a quiet system to get beta numbers, because some people can complain that some numbers at large scale are high, but it was mainly because, I repeat it, Stampede was in production. And it's not done, so we are still working on multiple things. So we discovered that there was an issue regarding PSM, to support PSM. So I'm currently working with one of the students of GI June to support OmniPass. We are also looking at working on a leader election strategy. So the idea is currently each MPI task is a checkpointing. So when you are doing a checkpoint at 24 or 32K cores, you have 32K cores that are writing in the same time. So the idea will be, instead to do that, try to reduce the number of streams on Stampede by 16. So having only 1 stream per node instead of 1 stream per core. This will the stream, the data transmitted to the stream will be higher, of course, because it will be an aggregate of all the other process. But we believe that it will make things much more scalable, because I don't know if Lustre in production can support this so big amount of MPI task writing. So that's all for my presentation. So if you have any question, feel free to let me know.
Jerome, thank you very much for a very interesting presentation. Do we have any questions from folks on the line? I'd be interested to see if this would be available on other platforms in Exceed besides Stampede, and also some of the campus champions on the line might be interested in how they can download such things for their user, because it sounds very generally useful. We all know of these long-running codes that have checkpoint problems.
So yes, DMTCP is not really available on Stampede, but it can run on Stampede, but it can work on any cluster. You just have to install it. The only downside that you have with DMTCP is that you will have to have 1 additional node for the coordinator. So you will have to request n+1 node for the coordinator. But any cluster, if you want to run Python code, R code, whatever, it will work with DMTCP, which is very nice. And we are currently looking to implement DMTCP on one of the cluster on Stampede called Ikari, that is running a lot of biocode that go always over the limit of 24 hours. So the idea is to checkpoint after 24 hours, checkpoint the code like this, the user can restart his code.
Yeah,
so,
great. Maybe I'll work with you offline to get some of the links for downloading them and getting them up on the Symposium website. So.
Yes, so there is a link for the MTCP on the slide.
Okay.
Here at the bottom, http://dmtcpsourceforge.net. So if you are interested, you can download here. If you have any questions, feel free to send me an email or to send an email to Jean, and I will try to answer to all your questions.
Yeah, great. Thank you very much. Sounds like a very worthwhile ECSS project. That's blossomed into much more. One more chance for folks on the call for questions.
Jerome, can you hear me?
Yes, I can hear you.
Okay. So, I mean, I saw that there was some kind of a large memory requirement for at least the NAS benchmark.
Mm-hmm.
I mean, what is the overhead typically for these, checkpointing processes?
So the overhead, I have some number here. So this is some for the NAS LE. As you can see, the overhead is very low for the checkpoint.
I mean, so in terms of memory overhead, I mean, so you meant I saw some
As a memory requirement, there is the memory required is. I mean, we don't have any issue. We were able to run HPCG with a size of 1.2 gigabyte per second. So it was times 16. I don't remember. So normally you have 2 gigabits per MPI per process on some PW. It's 32 gigabyte. So the memory required by the MCP is pretty low. It's not that high.
Okay.
I'm not aware about.
So you mentioned that an additional node is needed, so that whatever is available on that additional node should be sufficient for.
Yes. Yeah. Yes.
Okay. And so, I mean, so if you have this additional node, can an intelligent process be able to actually automatically restart these jobs?
So you can write a script that probably you can write a script that, I mean, it's very easy to restart a job with DMTCP. If you go on the DMTCP website, there is like a video that explains you how to use DMTCP, and you will see that it's pretty easy to restart a job, even a 24K jobs. So it's pretty interesting.
Thanks.
Yeah, Sudhakar runs the CGRID Science Gateway that runs a lot of computational chemistry code, so I'm sure he's really interested in this.
Yes. Thanks.
Okay, so Sudhakar, if you have more questions, you know how to contact Jerome, right?
Yes, if you want to learn more about DMTCP, feel free to contact me, I believe. No, there is not my email address. But
no, but there's a link on the symposium website.
Okay.
We have ways of finding other ECSSers. So
Okay,
okay. Thank you very much. I wanted to thank everyone on the call for staying over time, and thanking especially Kevin and Jerome for preparing such great talks for us this month. And hope to see some of you next month for the next ECSS Symposium.